Hello everybody, good morning all of you. My name is Kumar Anuj and I welcome you to Chandra classes. My dear friends, as you all know that in this entire series of lectures, the subject matter of our discussion is geography. And in geography, we are discussing about cosmology, meaning about universe, various aspects related to the universe, like the discovery of universe, origin of universe, composition of universe. So in our earlier lectures, we have thoroughly seen the discovery of the universe. First of all, various models associated with the discovery of the universe, like geocentric model, heliocentric model. Then after, we tried to explore about the origin of universe and various hypotheses associated with the origin of universe, like Big Bang hypothesis, oscillation hypothesis, steady state hypothesis. So we tried to comprehensively create a picture kind of how the universe was first discovered, then discovered by us, because universe was existing, but we got to know about the expand of the universe, about the extent of the universe. Very lately, before a few centuries, very few centuries. So once we got to know the vastness, the size of the universe, humongous size of the universe, then we tried to just dig in further and try to explore that how it got originated, because that humongous universe, it is not a small thing to originate. So how it got originated, what kind of things happened in the past, those created this universe that we are just seeing right now today. I present. So this was our matter of discussion in the second lecture, when we tried to explore deeply that how the universe was originated and various hypotheses. We just discussed the Big Bang hypothesis, which was the primary hypothesis, which is still considered the most precise hypothesis with respect to the origin of the universe, and with certain refinements as per the current understanding, scientific understanding or scientific enhancement. So largely we discussed about Big Bang and some other hypotheses, major hypotheses. But to sum up, the Big Bang hypothesis about the origin of the universe is a largely accepted hypothesis as of now. And it was saying that the universe originated around 13.8 billion years ago. 13.8 billion years ago. And this universe originated through the process of Big Bang. Though Big Bang is a kind of misnomer, it just says that there would have been some kind of bang, some kind of blast or explosion, but it was not like that. It was like a rapid expansion of the universe. The rapid expansion from the fields of energy. It was a rapid expansion of the universe. So then once the universe started getting originated, getting expanded, then after we saw that various stages of its development, like just to create a picture for the better understanding of our today's topic. So when it got originated, then first of all we see, for example, as the Big Bang hypothesis tried to talk, that there was a kind of cosmic egg. There was a kind of cosmic egg. Cosmic egg. So this cosmic egg, or primeval atom, primeval means the atom, the oldest atom, oldest known atom. So it was also known as primeval atom, called as primeval atom by George Lemaitre, who just propounded that particular theory, Big Bang theory. The Big Bang theory, the name was not given by George Lemaitre, it later emerged, but he talked about the cosmic egg or the primeval atom, meaning the oldest known atom, primeval atom, the oldest atom, the most primitive atom. So he said that cosmic egg, meaning primeval atom, went through a particular process like radioactive decay. Not exactly, maybe there would have been any other process, but he said like the process, as we know that the process radioactive decay takes place in unstable atoms, unstable nuclei. So when there is unstable nucleus of any atom, so to make it stable, the process of radioactive decay takes place. It is completely internal, spontaneous process. it does not need any external stimuli or agent to just, to ignite it. So cosmic egg, primeval atom. So he said, just kind of tried to simulate, George Lemaitre tried to simulate that a process like, exactly not, like radioactive decay, like radioactive decay, like radioactive decay, like radioactive decay, like radioactive decay. So we know that if there is any atom, it can be unstable, so there is not a big deal in that. So he said, since the entire mass of and energy, everything that we just know about the universe as of our today's understanding, it was compressed. It was compressed in that just single cosmic egg or primeval atom while the origin of the universe was taking place. So since the entire mass of the universe was just condensed in that particular primeval atom, so it could be unstable. The nucleus of the atom could be unstable. This is, can be related with, definitely related, can be related to the radioactive decay. So he said that a process like radioactive decay could have been taken place in the cosmic egg or the primeval atom. And as we know in the physics that the process of radioactive decay is the process which releases tremendous amount of energy. As we see that in the inner core of the earth, we know it very well that in the inner core of the earth, one of the most important sources of energy, because we know that the inner core of the earth is the hottest place in the interior of the earth, hottest place. It is around 5500 degrees Celsius, the temperature of the inner core, which we can try to equate with the temperature of the surface of the sun even. Because the temperature of the photosphere, the surface of the sun, is also around that, around 5500 to 6000 degrees Celsius. So the temperature of the core of the earth, one of the regions, not exactly entire region is radioactive decay, but one of the regions is radioactive decay, which is taking place inside the inner core of our earth, in the presence of some radioactive materials like uranium, plutonium, thorium, etc. So in the presence of those materials, the process of radioactive decay is also taking place in the inner core of our earth and generating tremendous heat. So when we talk about inner core, so inner core as compared to that cosmic egg in terms of density, temperature, just nothing, because the entire universe as we know today, it was just kind of compressed in that particular atom. So you can imagine the density, the compressive forces, the temperature maybe go beyond billions of degrees Celsius. So we don't know that in which form that atomic structure could be, because in that humongous temperature, we are not sure that in which form the matter could be. So we don't have any kind of exact clarity about that primeval atom. But if we try to simulate a process like something could have happened like radioactive decay, because this explains our understanding in a very systematic and precise way. So if any radioactive decay, the process of radioactive decay takes place, we know tremendous amount of energy is released. So it releases high powered energy, tremendous high powered energy, high powered energy, high powered energy. So it released high powered energy, and then after, when the high powered energy was released, then thanks to the Einstein, we know that Einstein said under his equation E is equal to mc square, that energy could change in the matter. This we know under the equation E is equal to mc square given by Einstein. So when tremendous high powered energy was released in the process, then some of that energy, not exactly entire energy, but some of the energy due to various circumstances could have been there. We are not familiar with all types of scenarios taking place back then. So some of the energy could have changed into matter. Some of the energy could have changed into matter. Could have changed into matter. How the energy changes into, I mean, how this entire process took place, how the matter took place. So, for example, when we see that high-powered energy remains in the form of photons, and photons created quarks and electrons. This is highly important timeline to have the broader understanding of the formation of the universe from the Big Bang to the formation of planets, solar system. So that's why it is very important. I just highly kind of stress over here so that you people are paying tremendous attention here and not missing any of the stages of the development. So under E is equal to mc square, we know the light, meaning photons, can change into quarks and electrons. And quarks are the fundamental blocks of the matter. As of our understanding as of now, quarks are the fundamental. I mean, there is nothing smallest beyond quark. So smallest particle existing, that is quark. And quark is the fundamental block of matter. So when quarks were created, so then quarks combined, these quarks combined to form the protons and neutrons. So these quarks combined to form protons and neutrons, and these protons and neutrons, they fused together to form nuclei. I mean, when we know that in the nucleus of an atom there remains proton and neutron. There may be only proton as well, but in most of the atoms it is proton and neutrons. And when protons and neutrons, they fused together, they form nuclei, because when there is a kind of protons in the atom, more than one proton in the kind of nucleus of the atom, so that nucleus of atom can become unstable. And to make it stable, one of the protons would have changed to neutron. So neutrons are compulsory to make balance, neutral balance in the nucleus of the atom. So that's why when protons and neutrons, they fused together, they formed nuclei, meaning in plural, nucleuses. So they formed nuclei, and later on, when the expansion, the universe got comparatively cooler, not exactly cooler as of our present understanding, but comparatively cooler, because when the origin, the Big Bang was taking place, it was tremendous amount of temperature, it was tremendously high temperature. But if when in later stages, when a little cooled down, then after the electrons attached to the nuclei to form atoms, light atoms, the light nuclei, light nuclei form. Light nuclei meaning hydrogen, helium, and helium, nuclei of hydrogen and helium. Because first of all, when any formation is taking place, the light amount of matter is being formed. So that's why light nuclei were formed, hydrogen and helium. And when the electrons got attached with these light nuclei, then they became complete atoms, atoms of hydrogen and helium. Hydrogen and helium. Now, when zillions of atoms were formed, zillions of uncountable atoms were formed, then they started just coming together in forms of clouds. Clouds. They started coming together in forms of clouds. Clouds of atoms. Clouds of atoms. Clouds of atoms. Which atoms? Primarily hydrogen and helium atoms. Clouds of atoms. When these clouds of atoms, they again compressed under gravity, they started forming stars. Stars. They started forming stars. And when a number of stars were formed, they combined together in the formation of galaxies. In the formation of galaxies. In the formation of galaxies. Remember, my friends, we are discussing very important concept about the origin, so that the picture is crystal clear. First of all, we must have the conceptual clarity before going into the details of the topics. So that's why this is building the conceptual clarity of our understanding that how the Big Bang theory, what we have earlier discussed as well in detail, but to have a revision, we are trying to just see the stages of the development, how the universe got originated in the conceptual basis, and how the other kinds of universal components like galaxies, like clusters of galaxies, solar systems, they were later formed, how stars were formed. So clouds of atoms, they compress together under gravity, because we know that each and every matter that is with the gravity in the universe, there is nothing without gravity. Even this pen, it also has gravity, but maybe it is having lesser gravity as compared to the earth. Of course, that's why when we leave it, it falls toward the earth, because it is having tremendously less gravity as compared to the earth. So that's why it falls towards earth. If it would have been having the mass more than earth and gravity more than earth, it would have attracted the earth towards it rather than falling towards the earth itself. So this is the fundamental kind of principle of gravity. So gravity is in every matter, atoms as well. So when atoms came together, they just started assembling in the formations of the clouds. And when the clouds further compressed under the gravity, they formed stars and galaxies. And when number of stars were formed, they again come together. The nearby stars again come together under gravity and formed galaxies. And when some of the galaxies, because we know the galaxies are very big, extremely big. So when some of the nearby galaxies, they combined together, combined means not exactly joined, but came together under each other's gravity and formed a group of, a cluster of galaxies. So that cluster, a number of clusters of galaxies were formed around the universe this way. Our galaxy, Milky Way, is also the part of a cluster of galaxy. It is very important. Which cluster of galaxy? It can be the part of any question in the competitive exam. Our galaxy Milky Way is the part of the cluster of galaxies known as local group. Local group. This is very important. The name is local group, and in that local group, there are around 30 galaxies, and our Milky Way is one of them. And this entire local group of galaxies, since it is bound by each other's gravity, it remains together and expands together in the universe. Just goes away in the universe together. These galaxies are not going further from each other. They are bound by each other's gravity and they travel in the universe together. So this was about stars and galaxies. And stars and galaxies, we know that stars, they have their own light. So from where they get their own light? They get their own light from nuclear fusion that takes place in the core of the star. Nuclear fusion. So stars, they have nuclear fusion. nuclear fusion in their cores to just get light energy illumination, because we know the stars are luminous objects. They have their own energy, not like planets. So stars are, they have their own energy, and their own energy comes from nuclear fusion that is taking place in the cores. So nuclear fusion takes place. But when the fuel ends up, for example, and one important aspect is also this, that when nuclear fusion takes place, because up to here we were seeing that light atoms, light elements like hydrogen and helium, they were formed, light particles were formed. But when nuclear fusion was taking place in stars, under tremendous compressive forces and heat and energy in the cores of stars, due to nuclear fusion, as we know, the nuclei of different atoms, they attach together to form heavier elements. So that's why heavier elements were formed. Heavier elements were formed. Heavier elements meaning oxygen, iron, oxygen, carbon, iron, silicon, etc. So some of the trace amounts, not exactly a huge chunk of heavy elements, trace amounts of heavier elements were formed in the cores of the stars because of the nuclear fusion taking place in the stars. Now, these were the stars, meaning with the atoms of hydrogen and helium, primarily more than 98%, and some trace amounts of heavy elements, But we know that stars, they have the nuclear fusion, the material nuclear fuel, because the nuclear fusion is taking place in the stars because they are having nuclear fuel. But once the nuclear fuel ends up, so they collapse. Once the nuclear fusion ends up, nuclear fuel ends up in the stars, they collapse under their humongous gravity. Their core collapses under tremendous gravity and gets blasted like a glass ball. For example, if we have a glass ball and we press it through any machine or any compressive forces, it would blast out and just get scattered all around. The dust particles get scattered all around. So similar thing happens with the stars as well. When they lose their nuclear fusion, meaning when they end up their nuclear fuel, then under their tremendous gravity, the core of stars, it gets compressed, massively compressed, and then the blast happens, and the entire material of the stars, meaning light elements, primarily light elements, hydrogen, helium, and some other trace amounts of heavy elements in the form of oxygen, carbon, iron, silicon, etc., they get scattered in the form of dust particles, gas and dust. Yani clouds of gas and dust. Clouds of gas and dust. And these clouds of gas and dust, because they are, again, these clouds, primary object is again the particles of hydrogen and helium, light elements, some trace amounts of heavy elements. So they again combine under the gravity to form new stars like sun, like our sun. So they again come together to form new stars. New stars like our sun. Sun is also, our sun is comparatively new star as compared to various other stars all around the universe. So they come together, the cloud of gas and dust, it again comes together under the gravity, and the formation of new stars, it takes place. Because we know for the formation of new star, any star, we need tremendous compressive forces. First of all, we need the humongous size of the matter. Then after that, humongous size under gravity creates tremendous pressure at the core of the object, meaning star. When tremendous pressure is created in the star, then the elements, meaning the atoms or the particles in the core, they start colliding each other rapidly. And the heavy temperature, the tremendous amount of temperature, millions degrees Celsius, that temperature is got created in the core of the stars, and they already have the nuclear fuel in the forms of hydrogen and helium, and the nuclear fusion kicks kicks in, it starts, and they start having their own energy and light. So that's how it takes place. So new stars were formed, they get formed, but some of the particles of this cloud of gas and dust, they just get scattered around this. They just get scattered around the new star in a form of a disk, a disk of particles of gas and dust. They just get scattered around the new star and start rotating. The disk start rotating, and when the rotation goes beyond the level, because this was entire new creation, and after the creation is complete, for example, star is having complete fuel, complete energy, everything, and after the increase in rotation, this matter in the form of disk which was around the rotating around the star, it starts getting clumped together. For example, the matter of this area getting clumped together, this area getting clumped together, coming together under gravity, and the rotational forces clumped together, again clumping together, and after clumping together, they form our planets around the star. How? When this matter clumps together, we know very well that this matter is in the form of gas and dust, meaning particles of hydrogen and helium and some other trace amounts of heavy elements like iron, silicon, oxygen, etc. Since the light elements, the gases, the light elements, they are extremely light, and they, just due to the tremendous heat of the sun, they are thrown away towards outer sides of the planet. They escape towards the outer sides of the planet, and they form gaseous planets. Since they are light gases, hydrogen, helium, they escape because they are light, they can escape, and they are also heated up, they can escape. So they escape towards outer sides of the planet, the formation of planetary systems, and they form gaseous planets. As we know, in our solar system, our gaseous planet, Jupiter, Saturn, Uranus, Neptune, they are known as gaseous planets. And the heavy elements like dust particles, meaning oxygen, carbon, iron, etc., silicon, etc., they clump together and form terrestrial planets. They form terrestrial planets. They form terrestrial planets. They remain close to the stars, meaning terrestrial planets. Those are made out of heavy elements like our Earth, Mars, Mercury, Venus, etc. So these terrestrial planets, since they have high melting point, tremendously high melting point, so they do not easily escape the proximity of the star, and they remain closely aligned to the star. That's why we see all the terrestrial planets of our solar system, they are inner planets. They are not thrown outside of the outer kind of solar system. In outer solar system, we have all other gaseous planets. Terrestrial planets are close to the stars because they have high melting point. They do not escape easily. They are made out of high elements. They do not escape easily. They are not easily blown out. So they remain close to the stars in the form of terrestrial planets, as we know now in our solar system, like in the forms of Mercury, Venus, Earth, Mars. All these planets are terrestrial planets. So that's how the entire thing from the origin of the universe. Now you can see from the origin of the universe up to the formation of planets. And our Earth is also one of the terrestrial planets. So from the origin of the universe up to the formation of solar systems and planets, this entire process takes place. So this was the idea which was expressed under the Big Bang hypothesis, that how the entire universe getting formed, and it is expanding as well. We'll be seeing later on how, when we were discussing about Big Bang theory, we saw that universe is not just so vast, it is also expanding and expanding in acceleration. So this is the entire idea framework, that how the universe just got originated, and other kind of components of the universe like many galaxies, stars, planetary systems, they were gradually step by step formed. So this could be a process under which our universe was formed. We are not having any kind of precise scientific understanding that how the origin of the universe took place, but we have some kind of idea based over our scientific observations that how it could have originated. So that's what we saw here. Now, this was for the broader understanding and to have a revision. But now the important point of today's discussion is the composition of the universe. Composition of the universe. Now, okay, we got to know that the universe was formed, but what is the composition of the universe? I mean, what are the main components of the universe? When we have anything, so we have the composition. For example, if we have this wall, particular wall, so in the wall we have some cement, some bricks, etc. A lot of composition is there, some sand, etc. So also there are a lot of components of the universe. We have three major components to discuss here. To just put all those components into those three segments to make it easier for you to understand. So composition of the universe. In the composition of the universe, you may be surprised to know. You will be surprised to know. आश्चर्य हो सकता है आपको जान के, because we see universe in the form of visible matter. हमें लगता है जो हमें दिख रहा है वही सारा universe है, all the stars, galaxies, all those kind of things, stuff around the universe we can see. That is entire universe. But that is only negligible amount of universe. All that what we can observe and see through our kind of eyes or aided eyes or electromagnetic radiation. So all those stuff, all that stuff, what we can see in the universe, that is only the fraction of the entire universe. Just you may get surprised to know. So let's see it. In the composition of the universe, the first important thing is dark energy. Dark energy. This is the first important major component of our universe, and this dark energy is around 70%. You may be surprised to know it is around 70%. 70% of the entire universe. 70% of the entire universe is this dark energy. So our entire universe, the 70% of the entire universe is made out of dark energy. And when we talk about entire universe, we are not just talking about the visible matter or the interactive matter. We are talking about the space as well, because space is also the part of the universe. When we go in space, so we are in the universe, that is also the part of the universe. So if we include entire space of the universe, entire expanse of the universe, and including all the material inside the universe in forms of atomic matter, if you include all those components, then we see that dark energy is the 70% of the entire universe. This is surprising. And the most important thing about this dark energy is that we first evidenced this energy in 1990s. we first evidenced this energy, sorry, we first evidenced this energy in 1990s. 1990s. This is known as dark energy because we do not have any proper understanding of the form of energy. That energy is in which form? We don't have proper understanding. That's why we call it dark energy. We can only just observe the impact of this dark energy, and that observation was first time observed, was made in 1990s during supernova explosions. Supernova explosions. As we have seen in our discussions, that when the nuclear fusion stops in the stars, meaning the nuclear fuel gets ended up, then the stars undergo through the process of supernova explosion. That is the supernova explosion. In that explosion, the core of the star that is getting bursted out. So when the supernova explosion takes place, they just release glow, stream of light, highly kind of visible spectrum of light, or you can say glow of light around it. So when the supernova explosions of certain stars were supposed to take place, I mean comparatively closer to us, and we were supposed to see a bright glow of light. हमें लग रहा था कि जो स्टार्स हमने पहले से आइडेंटिफाई किए थे कि वो हम सोच रहे थे कि वो हमसे नजदीक हैं अभी, क्योंकि हम अभी ये नहीं जान रहे थे कि यूनिवर्स जो है वो एक्सपेंड कर रहा है. हमें नहीं पता था कि वो एक्सपेंडिंग स्टेट में है और उसमें वो कैसे एक्सपेंड कर रहा है. अभी इतना हमें क्लियर आइडिया नहीं था, क्लियर पिक्चर नहीं थी कि वो कैसे, किस कारण से वो पूरी तरह से एक्सपेंड कर रहा है. We were not having any clear picture of that. We were having some observations from previous astronomers, but we were not having any clear evidenced picture of that. So when some of the supernova explosions, they were supposed to take place comparatively closer and with a glow of light, bright glow of light. But when they underwent the supernova explosion, the glow of light was dull. It was looking that it was far, I mean just at a tremendous distance as compared to sorry, our observations or our understanding. So जब हमने देखा कि उनमें एक्सप्लोजन तो हुआ, लेकिन वो लाइट जो ग्लो हुई वो तो बहुत ही डल लग रही थी, और हमने एक्सपेक्ट की थी कि बहुत ब्राइट ग्लो होगा, क्योंकि हम समझ रहे थे कि वो क्लोज है हमसे कंपैरेटिवली. तो हमने इससे अंदाजा लगाया कि वो जो स्टार्स हैं वो यानी हमसे बहुत दूर चले गए. हम तो सोच रहे थे कि हमसे नजदीक हमारे जो कैलकुलेशन के हिसाब से, लेकिन वो हमसे बहुत दूर चले गए थे तब तक. यानी वो ट्रेवल कर रहे थे. दे वर इन मोशन, दे वर ट्रेवलिंग, दे वर गोइंग अवे इन एक्सीलरेशन. And now we just started thinking that what could have driven those stars away and in acceleration, what could have driven. Then we reached to the conclusion that there is some form of dark energy in the universe, and that dark energy is not just at any particular location in the universe. That dark energy is spread in entire space of the universe, and as much as the universe is expanding, the dark energy is also getting created in similar amount. तो ऐसा नहीं कि यूनिवर्स अगर बहुत एक्सपेंड कर गया तो डार्क एनर्जी का लेवल फोर्स कम हो जाएगा. It is also increasing in the similar level, and that dark energy is driving our universe and expanding our universe in acceleration. That dark energy is responsible for the expansion of our universe in acceleration. We got to know in 1990s, and as we have discussed that this dark energy, mysterious form of energy. We don't have proper understanding that in which form, how it was created. Just we know it for our normal understanding that this dark energy could have been created during the origin of the universe. But how this could have been created, we do not have any precise idea. We just try to explore its origin in kinds of vacuum energy and various other kinds of theories, but we don't have any exact idea. And this dark energy, which was created during the origin of the universe, as we know, as we just think, that dark energy was not that much kind of active in the initial stages of the universe. But after few billions of years, this dark energy just became the dominant force, and in dominance force in the expansion of the universe, because it started driving, it started having driving accelerated expansion of the universe, accelerated 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 expansion of the universe, accelerated expansion of the universe. So for the accelerated expansion of the universe, this dark energy is responsible, which is the 70% of the entire universe. And we know that as much as the universe is expanding, the new matter is getting formed, and each and every object in the universe comes with its own gravity. So it means that gravity is also increasing in the entire universe. And gravity tends to attract the nearby objects toward each other. So if this would have been the case, if we just observe the universe without the presence of the dark energy, then with the increase of the gravity, the universe would have gone under deceleration. Should not be going under acceleration. It should have decelerated, because the gravity is increasing, the material is being formed. But it is not decelerating, it is accelerating, so that's why it proves that there is dark energy, and which overcomes the dark energies, meaning high impact, overcomes the gravitational forces. And that's why the gravitational forces became redundant in terms of the expansion of the universe. I'm not just saying that they become redundant in attracting the objects of the universe, but they fail to have kind of deceleration in the universe because of the overwhelming force of dark energy, which is expanding the universe. So this is the dark energy. It is 70%, as we know. It existed since the origin of the universe, but became dominant after later stages of the development of the universe, meaning after a few billions of years, because we know the universe was formed around 13.8 billion years ago. So after a few billion years, maybe 5-6 billion years, this dark energy became dominant force. And this dark energy is everywhere around the universe, because it is in the space all around the universe, maybe in the form of vacuum energy, because our understanding is very limited. That's why we call it dark energy. Okay, so this was the first important component of the universe, dark energy, 70%, around 70% alone, from 68 to 70% alone. Then after we have another strongest component, that is dark matter. That is dark matter. That is dark matter. And this dark matter is around 25% of the entire universe. Why do we call it dark matter? Why do we call it dark matter? Just we have to raise it to get some space to write down the new ideas about the dark matter. So we call it dark matter. We call it dark matter because it does not emit it does not emit it does not emit it does not emit sorry, absorb or reflect light. That's why we call it dark matter. It does not interact with the light overall. For example, we know about the matter. For example, this a table, chair, wall, etc. All these matters, they interact with the light. That's why we can see them, because they are interacting with the light. But dark matter, it does not interact with the light. Neither it emits light, neither it emits light, neither it nor it absorbs light, nor it reflects it. So that's why we call it dark matter, because it does not interact with the light. Then if it does not interact with the light, it means we cannot see it. Then how we could know about the existence of this matter? We know about the existence of this dark matter because of its humongous gravity, because it is finally, at the end of the day, it is the matter. And we know that every matter in the universe, it comes with the gravity. So if there is a dark matter, it would also have gravity. So we observe the impact of the dark matter because of its tremendous gravity in various galaxies and various kind of cosmic events. So we know about the existence of this dark matter because of its gravity, humongous gravity. Because if we observe, we see the gravity of the sun, which binds the entire solar system together, is so humongous, while the sun is just a particle of sand on the beach in the universe. If we just compare the size of the sun in the universe, it would be like a particle of sand in a big beach, on a big beach. So that is only the tiny size of the sun. And here we are talking about 25% of the component of the universe. Although this 25% component, this dark matter, is not clumped together. It is not entirely clumped together. I mean, 25% chunk is here, not like that. This dark matter is scattered all around the universe, but in certain amounts, still bigger than various objects, various celestial objects. So it implies tremendous gravity and pulls nearby objects, and that's how we get to know about the presence of dark matter, because of its humongous gravity. If it would not have been having gravity, it would be very tough for us to understand the existence of any dark matter, because it is not visible, it does not interact with the light. So that's why thanks to the gravity the dark matter is having, so that's why we can recognize its presence in the universe. So that's it. It doesn't play any big role, other than gravity, because it has gravity, so it interacts with the nearby components, nearby objects in the universe under the gravity, can pull various objects. So this is all about dark matter, the second most important component of the universe. Now we just talk about the third component, which is going to be the most interesting component, that is baryonic matter. And this baryonic matter is around only 5%. This baryonic matter is around only 5% of the entire universe. This baryonic matter is around 5% of the entire universe. Now let's break it down. Now we should break this down, this baryonic matter, in the next slide. Baryonic matter. So we are going to talk about baryonic matter, which is around 5% of the entire universe. This is baryonic matter. And the baryonic matter is that matter which is made out of particles, different particles, meaning for the simple understanding, we can say that this is atomic matter. Maybe some of the matter may not be in the atomic form, maybe in plasmic form, maybe in the form of particles like proton, neutron, etc., electron, separated from each other. So largely and simply speaking, that this baryonic matter means, when we talk about baryonic matter, it means that atomic matter, all those materials that are made out of atoms, they come under the category of baryonic matter. It means our entire planets, our stars, they are the galaxies, clusters of galaxies, all those components in the universe. So that we can see either through naked eyes or with the aided eyes or with the electromagnetic radiation. All those components, in the universe, so that we can see. Not, I'm just talking about with the naked eyes, meaning we can see with the telescopic observations electromagnetic radiation. So all those matters all around the universe, they fall under the category of baryonic matter. And now you see that what the extent of this baryonic matter is, only 5% of the universe, to which we were understanding that it is making the entire universe, but it is only the 5% of the universe, only 5% part of the universe. More than 95, around 95% of the universe is still highly unknown in the form of dark energy and dark matter. We don't have any proper or good understanding about dark energy and dark matter. We just know that they exist because of their impacts. The impact of dark energy in accelerated expansion of the universe, the impact of dark matter in gravity. So that's why we can observe that they exist, but we do not have proper understanding or in-depth understanding of those components. But here, baryonic matter, of which we have some understanding, that is only the 5% of the universe, to which we people largely understand that it is the entire universe. This is only 5%. For our better understanding, now we should break it down. This baryonic matter is made out of light elements, light elements and heavy elements, heavy elements, light elements and heavy elements. Because we categorize the elements in two categories, light elements and heavy elements. Light elements are only two elements, hydrogen and helium. Light elements are those elements that have maximum 2 nucleons. And we know that hydrogen protein atom, it has just 1 proton in the nucleus. Helium, 1 proton, 1 neutron. Helium, 2 protons, 2 neutrons. So all that matter, I mean the atoms of the matter, the nucleus of the atom, they have maximum 2 protons. That is known as light element. And in that category, we find hydrogen and helium. Hydrogen and helium. Light elements, these are the only 2 light elements. All other elements, those are heavier or heavy elements. Oxygen is also heavy element because it also has more than 2 protons in the nucleus. Hydrogen and helium, and in this entire baryonic matter, the share of hydrogen is around 74%. The share of hydrogen is around 74%. 74%. I mean, in this entire baryonic matter as well, 74% is only the hydrogen in this entire baryonic matter. And to your surprise, 24% is helium. Meaning, this baryonic matter is only 5% of the entire universe, and in that entire baryonic matter, 74% is hydrogen and around 24% is helium, meaning light elements 98%. 98%. This is very important to have the conceptual understanding, because now we know all the baryonic matter, all the matter that we can observe, we can see, that is primarily made out of light elements, because they are 98% of the entire baryonic matter. So that's why we should not be surprised when we see various galaxies, stars, etc., they are made out of light elements because the major huge chunk of share of the baryonic matter is light elements. Hydrogen 74%, helium 24%. And when we talk about heavy elements, it is around 2%. Heavy element, it is around 2% of the entire baryonic matter. More than 2% in the entire baryonic matter. Heavy elements meaning the nucleus having more than 2 protons. Those materials, the nucleus of which having more than 2 protons in it. So those are known as heavy elements, and they are only 2% of the entire baryonic matter. Heavy elements, as we have talked earlier as well, like oxygen, iron, carbon, silicon, all these materials are the heavy elements, are made out of heavy elements. And all that matter, for example, our earth, if we just talk about our earth, it is primarily made out of heavy elements, fraction of light elements in the form of hydrogen, in form of outer layer, etc. in the atmosphere. So we see the earth, which is primarily made out of heavy elements, it falls under this category, which is less than 2% of the entire baryonic matter, and our earth is one of that. Our earth is also falling in this material category primarily. So these heavy elements, all that matter that we can visibly see, for example, and also gases are also included. Those are kind of heavy gases, meaning the gases made out of heavy elements. But visible materials are also included, like iron, like silicon, etc. So this heavy element, this component is the most important component for the existence of the human being. Have you ever thought about that? Existence of the human being depends on heavy elements. If there would not have been heavy elements, we would not be having iron, silicon, oxygen, carbon, etc. Meaning we would not be having the earth at all. Almost earth at all. So if we won't be having earth at all, then our existence, there was no any question of our existence. We were not existing. So that's why this component of the universe is very crucial for the existence of the life. And we are also the part of heavy elements. We are also made out of heavy elements. So the living entities like human beings, vegetation, etc., they also fall under this category under 2%, in the 2%. So entire kind of our earth and its life, it is because of this 2%. So that's why this 2% is very important for our survival as well, not for our study and our exams. So that's how we get to know about the composition of the universe, in tremendously detail. And this is going to build up conceptual basis for our further understanding in next lectures, because this is putting the foundation. Now we have the crystal clear picture about the composition, about the origin, discovery, etc. All those things about the universe, if we just look into our lectures discussed till now. So that's it all for today, and excited to meet you again in the next lecture with new topic. Thank you very much for joining in.